So hello everyone. So welcome for this second live session for this course Fundamental of Bioprocess Engineering. So today we'll be covering the topics related to week 5, 6, 7, and 8. So I see in the chat box as of now there is no query. So you please share your query if any in the chat box. I will be able to answer here. In addition, what I'm doing, I will go through these assignment questions of these weeks so that we will keep discussing. Now, week 5 was microbial kinetics. So we'll start with week 5. So the first question was, which enzyme is used in ATP assay for bacterial cell enumeration that produces bioluminescence? So here options were amylase, liqueface, peroxidase, and catalase. So as you know, amylase hydrolyzes starch into sugar. Peroxidase, it catalyzes the reaction with hydrogen peroxide. And catalase, it decomposes the hydrogen peroxide. So only option is luciferase, and if you remember this luciferase, it catalyzes the reaction of ATP with luciferin, and it produces a light or is a bioluminescence. Moving ahead, question number 2, it was production of citric acid was done by using filamentous fungi Aspergillus niger in a submerged bioreactor. The growth of fungal pellet occurs under surface limited conditions. The initial mass was calculated as 0.5 mg, and through the proper experimentation and calibration, the value of growth constant was found to be 0.6 mg to the power 1 by 3 or to the power -1. Now we need to find out the expected mass of an individual pellet after 5 hours of cultivation under these conditions. So before we go ahead, if you remember, we discussed this. The growth kinetics can be segregated and unsegregated, structured and unstructured. So what is the difference between this segregated and unsegregated, structured and unstructured? So one considers cell heterogeneity and other considers the average cell approximations. So when we are talking particularly this growth of filamentous fungi, so here, if you remember, we also discussed the biomass can be reported in terms of number or in terms of density. But for this case, it's very difficult to report or measure in terms of number. So here we have to measure in terms of mass or density. Now, if you remember, for such cases, we discuss what should be the mass. So mass will be equals to the initial mass to the power 1 by q plus gamma. Gamma is the growth rate constant into time. How much time you have to calculate? 5 hours upon 3 to the power q. And if you put this value, we'll get m as 5.77 milligram. So in 4 hours, the biomass will grow from 0.5 mg to 5.77 mg. Now in the third question, Which of the following statement is true regarding substrate affinity constant Ks? So if you remember monad equations, it says mu as mu max S upon S plus S. Now this Ks indicates the affinity towards the substrate. So it says which of following statement is true. So low Ks indicates low substrate affinity and requires high substrate level for efficient growth. B option is high Ks value indicates high substrate affinity and enables maximum growth rate at low substrate level value. Third option, low Ks value indicates high substrate affinity and enables near maximum growth rate even at low concentration. So it says if Ks value is low, it means it reflects the high substrate affinity, and in fact, if Ks value is low, it means this equation can be simplified as mu equals to mu max. So it enables near maximum growth rate. Now the question 4, which of the following microorganisms requires light for its growth? So for that, it's very obvious the cyanobacteria is a photosynthetic microorganism, so that will require the light. Next question, which one of the following is not a function of carbon source present in bacterial growth medium? So carbon source acts as a source of energy used for the maintenance, used for product formation, but cofactors are typically they are non-carbon compounds, includes metal ions or organic molecules like vitamins. Next question, which of the following factors cannot affect the growth of an microbial culture in a batch cultivation process? So if you remember, in a batch cultivation mode, it is a closed system. There is no inlet and there is no outlet. So if there is no inlet means the substrate feed rate is not going to affect the microbial growth rate there. While the pH may affect, osmolarity may affect, and substrate concentration is definitely going to affect. But as it is a non-continuous process, it means the inlet and outlet is 0. Next, you have to match microorganisms with their suitable applications. So there, most common one is the Aspergillus niger. It produces the citric acid. Now comes the ethanol. It is again obvious the Zymomonas mobile produces the ethanol. Now comes these two products, single cell protein and iocyanine. So for single cell protein, SCP, we use this Chlorella vulgaris, and Pseudomonas aeruginosa can be used to produce phytocyanine. So option C is correct. The next question is a batch fermentation process for the production of ethanol was carried out by Saccharomyces cerevisiae. Ethanol concentration in the media reaches 11% after a few hours, at which the cell started to lose the cell viability. It means along with the growth, now cell death kinetics also need to be considered and assume the KD value as 0.12 our inverse. The maximum specific growth mu max is 0.2 our inverse. Kx value is again given as 0.3 gram per liter. Substrate concentration is 5. Calculate the net growth rate. So typically, what happens? Mu is defined as mu max S upon Ks plus S. Now here, what you have to do? You have to subtract the Kd value. Now all the parameters are given here. So you can put these parameters over here. So you get answer 0.25 our inverse. 0.26 our inverse is the correct answer. Now next question is specific growth rate is given and you have to calculate doubling time. So this is very straightforward. It says doubling time is defined as ln 2 upon mu, and you put the value, you get specific growth rate as 1.386 our inverse. Next question is equally inoculated in a safe pass containing nutrient-rich medium. The initial number of viable cells is 10 to the power 2. And after a few hours, the number of viable cells is 10 to the power 6. There is a growth. Now assume the cell divides by the binary fission. Means one cell is divided to the 2 cells. Now calculate the number of generation. So this is again very straightforward. It says number of generation is ln n upon n naught divided by ln 2. Now n is 10 to the power 6, n naught is 10 to the power 2, so you got n is a 13th generation. So after 13th generation cycle, 10 to the power 2 cells will reach to the 10 to the power 6 cells. So this was all about this week 5. Let me see if there is any query online. So far there is no query. So what we'll do, we'll go ahead with week 6 now. The week 6 is related with kinetics of substrate utilization, product formation, and biomass production in cell culture. So here we started with the structured kinetic models. So we discuss different types of structured kinetic models, and followed by that we discuss substrate utilization and product formation. Now, the first question is which one of following is not a limitation of unstructured kinetic model used in bioprocess models? So it says the unstructured kinetic model does not require the detailed knowledge of metabolic pathway or cellular structure. What does it mean? It means it treats cell as a black box. There is some inlet and there is some outlet. Our substrate is coming, it is converted to product. So it says the requirement of detailed knowledge of metabolic pathway and cellular structure is not required in the case of unstructured kinetic model. Now, which one of following mode of operation does not work based on the structured kinetic model? Now, if I say the structured kinetic model means we are dealing with unsteady state. Now, if we consider transient situation, unsteady state, batch is unsteady state, fed batch unsteady state, while continuous is the steady state. Now question 3, if relaxation time of some cellular processes are very large compared to the relaxation time, they are generally assumed to be, so what it says, when there are some processes going on and in between some cellular processes are also going on. Now which one to consider, which one not to consider? So what we say typically, if the ratio of small relaxation time to the tau E is small, then we say it is a kind of quasi-steady state. But if for some cellular process the very large, then we can ignore and we assume that they are in a frozen at initial state. Because after the certain changes also, they will, because of the large relaxation time, they will still be in the same state. Now next question, which one of the following component is directly proportional to cell number density according to Williams two compartment model? So you remember the Williams two compartment model? So it has the structure, genetic component, and the component 2, the component 1 is a synthetic component, and component 2 is a genetic component. So we discuss in terms of row 1 and row 2. And what it says that cell number density is directly proportional to the structured genetic component, or you can say this is a component compartment 2 of Williams two compartment model is produced from the component 1, that is the synthetic compartment of the cell density model. The next question is, which one of the following is not a product of anabolism? So catabolism means breakdown, anabolism means synthesis. So lipids can be synthesized, and DNA is biosynthesized, carbohydrates are biosynthesized, while carbon dioxide is usually a waste product of catabolism. So correct answer is D. Next question is, which is the end product of yeast fermentation under glucose limited condition when mu is less than the mu critical? If mu is less than mu critical means the process is said to be fully respiratory, and therefore metabolic shift will be toward the production of biomass and carbon dioxide. While when mu is greater than mu critical, and then it becomes anaerobic process, and then metabolic shift is shifted toward the production of ethanol and carbon dioxide. So in this case, there will be synthesis of biomass in a good quantity. Next question is, a microbial fermentation was carried out to produce inulinase enzyme. Now what it said, the initial cell concentration at 0th hour is 0.23 gram per liter, and which increased to 4.78 gram per liter after 6 hours. What is the total product form after 6 hours? It gives the value of alpha as 0.75. So if you remember, we discussed in this case the rate of product formation dT upon dt has a two part. One is the alpha, which is growth associated part, and the beta x, this is a non-growth associated part. So what it says here is a growth associated product, because along with the growth, there is an increase in the product formation. So alpha is given to us. For time being, we can ignore this beta part. So we consider this dp upon dt is alpha dx upon dt, and if you can integrate p from the time is range from the 0 to 6 hours. So this should be delta x and delta p. So we are assuming p naught is 0. So we directly get the p6 at alpha into delta x. Delta x is 4.78 minus 0.23. So the correct answer will be 3.41. 3.41 gram per liter. Our next question is an antibiotic producing bacterial fermentation enters the stationary phase at 8th hour. Okay, and it extends till 13th hour. Okay, and the antibiotic concentration at the early stationary phase is 0.97 gram per liter, and it reaches to 3.47 gram per liter. So again, it is a non-growth associated product, because here the growth is taking during the secondary phase. You can say it is secondary metabolite, and biomass concentration remains constant at 2.5 because it is stationary phase. What is non-growth associated product coefficient beta? You have to calculate. So here again you have to use the same formula. It's a dp upon dt is equal to alpha dx upon dt plus beta into x. So this term is 0 here. You get beta as dp upon dt divided by x. So x is 2.5 gram per liter. dp upon dt is, we can write delta p upon 30. You get beta as 0.2 our inverse. Our next question is a batch fermentation involving the production of penicillin using Penicillium chrysogenum. The concentration of penicillin was found to be increasing at the rate of 0.085 mole per liter per hour. The molar rate of penicillin formation by the culture is 0.2 mole per liter per hour, and the concentration in the reactor is 1.2 mole per liter. Now you have to calculate what is the dilution rate. So it says this change in the concentration dCj upon dt equals to RFI rate minus mu into Cg. And what you have to calculate? You have to calculate the mu. So mu will be RFI minus dCi upon dt divided by Cj. So all the parameters are given here. If you put this into this formula, you get mu as 0.096 hour inverse. This is the correct answer. Our next question is related with Ramakrishna two-compartment model. So it says, which of the following is not a component of G pool? So if you remember in the Ramakrishna two-compartment model, G mass constituents RNA and DNA, and D mass constituents only proteins. While in the Williams two-compartment model, one compartment includes is DNA and protein together. Now, what are the options? Yes, proteins. The proteins are not a component of the G pool. And it includes nucleic acids. With this, now we go to the week 7. Again, there is no query so far. So we'll go ahead with the week 7 questions. And the week 7, the first question was, so week 7 is related with design and analysis of biological reactors. So there, we discussed the batch, fed batch, and continuous operation of bioreactors using pre-cells, immobilized cells, pre-enzyme as well as immobilized enzyme. In addition, we also discussed the packed bioreactors. The first question is which one of the following condition is correct about the chemostat operating with cell recycling? So typically, what is chemostat condition is mu equals to D, and when you can exceed the D greater than mu, it means it is coming through the cell recycle. The cell recycle, you can operate allow the dilution rate greater than the mu without the washout. Question 2, in the continuous fermentation process, the biomass concentration can be maintained without washout, without being washed out of the system, can be achieved by maintaining. Then the term says the dilution rate should be below the critical dilution rate. So if it is below the critical dilution rate, so we can maintain the desired concentration of the biomass. And if D exceeds the mu critical, then it proceeds towards the washout. It means there will be no cells in the bioreactor. X becomes 0. Next question is, which one of the following is not an advantage of performing fed batch? So why we perform the fed batch? Because if there is substrate inhibition, you cannot add all the substrate at a time. And if you want to achieve the high cell density, you go for the fed batch culture. At the same time, if there is a formation of undesired metabolites, you want to remove it, or you can say you want to tackle the inhibitor or the product inhibition. In that case, also use the fed batch. Only the incorrect option is delayed production onset, because delayed production onset is a drawback of fermentation process. It implies slower or the postponed start of product formation. Instead, the fed batch aim to prolong the productive phase and enhances the productivity. So option D is not correct. Next question is a batch fermentation for the production of food coloring by Monascus for Curious was inoculated with biomass concentration of 0.25 gram per liter. The specific growth rate of microorganism is 0.79 hour inverse, and KD is again given 0.06. Then it says what is the biomass concentration after 6 hours of the batch culture. So we know in the case of batch culture, X is given as X is X naught e to the power mu t. Now this will be replaced by X naught e to the power mu minus kb into t. So you get X as 86 gram per liter. Next question is, a fed batch process is running at quasi-steady state with respect to substrate and biomass concentration. At 3 hours, the culture volume is 450 liter. with a constant sterile inlet feed rate is giving 65 liter per hour of infusion. The kinetic parameters are given mu max and Ks. Mu max as 0.25 hour inverse and Ks 0.07 gram per liter. The substrate concentration in the bioreactor we can find out. Now it says the fed batch at the first steady state. So in that case, the substrate concentration is given as D into Ks divided by mu maximum minus D. So all the parameters are given. What will be the D? D will be F upon V. Flow rate is given. D will be F upon V 0.14. Now the S will be D. Ks is 0.07. Mu max is 0.25 minus D 0.14, and then you get the answer as 0.1. So going ahead, question number 6. In a chemostat, the dilution rate is 0.55 hour inverse. The steady state biomass concentration and specific product formation rate are 4.3 mole per meter cube and 0.15 moles of product per mole of biomass per hour. I have to find the steady state product concentration in the mole per meter cube. So this is chemostat. So we know P is QP into X upon D. So QP is given as 0.1. Biomass concentration 4.3 mole per meter cube. And dilution rate is 0.55. So you can get the product concentration as 1.17 mole. Next question is the chemostat with the shell recycling. Now in this schematic it says F1 is entering, F0 is existing, and FR is getting recycled. So it says this in this junction you are having the inlet as F0 plus FR. So FR is going out and F0 is going out and FR is recycling. Now the ratio is given as X0 upon X1 as 0.75 and FR upon F0 as 1.2. And the value of X1 here is given as 9.2 gram per meter. I have to find the value of X, which is the mole system. It's very straightforward because if X1 is given, we can quickly find the value of X0. And then by doing the simple material balance, we can get the value of X. So it says the simple F0 into FR into X1. This equals to F0 into X plus FR into X0. Now this FR I can write in terms of F0, and again this X is unknown, and this X0 will be 0.75 into X1, 6.9 gram per liter. So X0 is also known. FR again you can write in terms of 1.2 F0. So ultimately you get this expression in terms of F0, and F0 will be cancelled out here. So we'll get the X as 11.96 gram per liter. Our next question is, which one of the following is not a typical application of plug flow bioreactor? So PFR is typically used in the petrochemical processing. In the PFR, we say there is no lateral mixing. So it is used for polymerization reaction and waste treatment. So it is not used for the enzyme production. For the enzyme production, typically is performed in the CSTR or in the batch mode. Ninth, in a chemostat, the feed flow rate and the culture volumes are 200 and milliliter per hour and 1.5 liter. With glucose as substrate, the value of mu max and Ks are given. For a glucose concentration of 8 gram per liter in the feed, the effluent substrate concentration in gram per liter. So it says yes, I is given to you and yes, out, you need to find out. So it is a simple mass balance here. So it says mu equals to D and D equals to mu, and mu is defined as mu max S upon Ks plus S. So from here, you can quickly get the value of S, and S is coming out to be 1.8 gram per liter. So 1.8 gram is in the bioreactor, the inlet is the 8 gram. What is going out will be 8 minus 1.8 equals to 6.2 gram per liter. 6.2 gram per liter. Now question number 10. The phenolic wastewater discharged from an industry was treated with Pseudomonas species in an anaerobic bioreactor. Effluent concentration of phenol, so inlet and outlet concentration are given to you. The inlet feed rate was 60 milliliter per hour. Maximum specific growth rate and the mu max and Ks are also given here. The process, provided it is working under chemostat, it is a continuous mode of operation, right? So again, it's a very straightforward question. So it says you can find the value of D or mu as 0.1163 our inverse. But here the death rate is also given here. So the net growth will be mu minus AD. So this will be 0.1063. And once you know this mu or D, so this become D is equal to F upon V. So D will be F upon D. So only what you have to do is for calculating the D, we have to change mu minus 8. So with this, I think we concluded 3 weeks. So let me see if there is any other. So there is no question in the chat box. So now we can quickly go ahead with the week 8 questions. So that is gas liquid mass transfer in the bioprocess. So in this week, we mostly discuss about this aeration and agitation process. So the first question is, this Saccharomyces cerevisiae is cultivated in 5,000 liter aerator steel tank bioreactor for bioethanol production. At steady state oxygen transfer condition, the specific oxygen uptake rate Q naught is given and volumetric mass transfer rates are as the Q naught is 2 into 10 to the power minus 4 gram oxygen consumed per gram biomass, and KL is 18 minute inverse. Oxygen solubility is at equilibrium is 8 ppm or 8 into 10 to the power minus 3 kg per minute. Now you have to calculate the value of maximum possible same concentration. So we calculate the maximum possible. We consider the whole concentration of oxygen is utilized for the biomass growth. So if you remember, the formula for mass transfer is Na A C Cn star minus Cn. Now in this case, if you put this Cl as 0, so it becomes Kna C star that is equal to Q naught into X. Now once you put this Cl 0, the X is replaced by X max. And this X max, all the parameters are given to you. You can quickly calculate it. Next question is the biofuel broth is mixed with 5,000 liter stirred bioreactor using a Ruston impeller of diameter of 0.8 meter. The broth has a density of 950 kg per meter cube and viscosity 2 centipoise. And the RPM is given as 240 RPM. The correlation between power number and impeller is for given value of Reynolds number, there is a different value of power number. So you have to calculate the power. So for that, first you have to calculate the Reynolds number. Then you find the value of power number. And once you get the power, then depending on laminar or turbulent flow, you can calculate the power requirement. How you get the Reynolds number is Re as Ni di square rho upon mu. So you got turbulent flow 10 to the power 6. So NP will be 5. Power number is 5. Now for the turbulent region, you know P is rho NP NIQ Di 5. So you get the power requirement will be 100 kilowatt. Next question is in a bioreactor, oxygen bulk concentration is 8 millimole per liter and interfacial concentration is 2 mole per liter. Okay, so it is decreasing from bulk to interface. And K is given and mass transfer coefficient is given 2 into 10 to the power minus 4 meter per second. Interface area is also given A. We need to find the oxygen transfer rate. So straightforward, it's K into A, CAB minus CI. So delta C is the driving force. And you get the answer at 0.24 millimole per liter. Next question is, if diffusivity of glucose in water is 6.9 into 10 to the power minus 10 meter square per second, and the concentration gradient is 4 mole per meter cube. What is the flux? It's again, it says it is following the Fick's law of diffusion. So J is equals to DAB is given to you and dCA upon dy. The dCA upon dy is given as 4. DAB is 6.9 to the power minus 10. You get the flux as 2.76 10 to the power minus 9. Now this question 5 is based on the method used to calculate the KLa value. So at 2 different time points, you measure the concentration of oxygen or the air saturation. Now, if you want to calculate the KLA value, the formula is very straightforward. It says KLA as ln CL star minus CL1. So CL1 corresponds to the concentration at a one time point, and CL2 corresponds to the concentration at second time point. So it's a 40 and 60, and delta T is the difference in the time. It was 15 and 5. We'll get straightforward KLA as 0.0693 seconds. Next question is, a microbial strain is cultured in a 200-liter steel tank bioreactor for antibiotic production. The specific oxygen uptake rate Q0 is given to you. Oxygen solubility in the broth is Cl star is given 8 milligram of oxygen per liter, and the process aim to achieve the maximum cell concentration X max is given at 20 gram per liter. Assuming the dissolved oxygen concentration in the broth is nearly 0 at the 15 month, right? The minimum volumetric mass transfer coefficient KLA. So again, this is a straightforward question. So this will be KLA equals to Q naught X upon CAL star. The similar equation which we used earlier. So if you put the CAL is 0, then X is replaced by the X max. So you get the value of KLA as 0.556 seconds. Next question is, in a 500-liter steel tank reactor, Ruston turbine impeller is used to agitate an unaerated Newtonian bath. Okay, the system is operating in a fully turbulent region. For this configuration, how the power depends on the impeller speed. So for turbulent, you know this power is proportional to Ni cube di5. So P is proportional to e to the power cube. Next is how the Reynolds number is defined. So we already discussed that Reynolds number is equal to rho V d upon mu. The rho is there, V will be replaced as N I di, and D is again replaced by di upon mu. This becomes Ni di square rho upon mu. This is the NP. R is the Reynolds number. Next question is, in aerobic bioprocess, oxygen transport from gas bubble to the cell has multiple steps. So you can 7 or 8 steps. Out of these, the maximum resistance to mass transfer is usually encountered in the, so it counts maximum resistance in the film tube. And the film is stagnant liquid film around the gas bubble. So crossing that step, and typically if you remember, this is a third step. What is the first step? First step is transport within the gas phase. So let's say this is the cell. This is a gas bubble. In the gas bubble, the first step will be transport from within the cells to this cell surface, or the gas bubble surface. Then it crosses the second step is this, and then third step it is crossing the liquid film. Then here it is facing the film resistance, and that contribute to the maximum mass transfer resistance. So step 1, step 2, step 3. Now next question is, in an oxygen transfer experiment, increasing agitation speed improve the transfer rate. So if we are increasing the agitation speed, it is improving the transfer rate. So if you remember, the transfer rate Na is PNA Cl star minus Cl. What you are doing, you are increasing the agitation. It means you are not changing the concentration part. It means you are improving the KLa. In fact, what we have discussed is if you remove if the mass transfer coefficient K is depending on the not only this agitation speed, it is regulated by the hydrodynamic property of the flow. In fact, there is a correlation between hydrodynamic parameter and the K. And K is coming in the terms of Nusselt number. Now K is coming in the Sherwood number. So with this, let me again see if there is any other query. So there is no query in the chat box. Is there any query in the Excel sheet? There is no query. So with this, I think we can conclude this second live session. So thank you so much, everyone. So we'll have one more live session. So if you have any query or doubt, please let us know. We'll be able to address those in the next live session. In the meantime, again, if you have any doubt, then please share in the this email in the forum, and we'll be able to address those queries. Thank you so much.